Hi, welcome to this use case demonstration of AM gripper attached to a robotic arm. The aim of this session is to understand how different stages of product development or various courses that we have learned before can be applied to the end-to-end development of an AM workflow. So let us first define the jobs to be done in this whole development process. First, you need to define the specifications for the product. What functionality do you need? What materials can you use? What are the loads acting on the system? These should be structured and properly defined. A CAD designer's job is to find the right form of the product. They should create a parametric design space the new geometry is allowed to take in such a way that it should be adaptable to the different versions of the non-design spaces. In this case, there are two different versions of the gripper geometry that has to be created such that it is automatically adapted to the respective non-design spaces. An FAM engineer should analyze the created part for the given loading conditions and materials to evaluate the stresses and displacements. An optimization specialist should reduce the mass of the given part based on the specifications and FEM analysis. This makes the design lightweight, as the gripper should not add too much mass to the robotic arm it is attached to. This also reduces the cost of manufacturing of the part. The CAD engineer now needs to create a final design out of the optimization result. They should reconstruct the result such that the non-design spaces are smoothly connected to the new lightweight form. As we are creating a workflow for a vacuum gripper, there is another job to be done: creating pipes in the final design. They should be short and optimal between the vacuum plate and the suction cylinders. After creating these pipes in the optimized geometry, we have the final design ready for additive manufacturing. An AM process engineer now prepares and optimizes everything for manufacturing. They perform an evaluation study and estimate the KPIs such as the mass of the final part, cost of manufacturing of the part, and AM process simulation to analyze the residual stresses, displacements, and calculate a pre-deformed part to compensate these distortions. We can clearly see that there are different stages of the product development process, each of which has their own specialists involved. And this is how it looks like if everything is connected together and the whole workflow runs smoothly across the stages. Let's have a closer look at the development of this workflow using connected engineering approach. This workflow is clustered into different stages, each of which has a workflow included with inputs and outputs. As you can see here, these are the different steps with workflows included in them. So let's have a look at one of the steps, which can be the first step, where we are importing the input data. So here we define the paths to the non-design spaces, that is the vacuum plate and the suction cylinder. And here we also import the specification sheet that has the loads and the materials information. And here we also selecting different materials that can be used for this development process. So let's go inside this workflow and see how does it look like. So here we can see in the first stage we are importing these suction cylinders, which are the non-design spaces based on the use case that we have selected. So here we have two different versions of the suction cylinders, one with 6 and the other with 8 number here. So this is with 8 number. And here we also import the vacuum plate, which is common for both the use cases. And then here from the specification sheet, we are importing the materials data, such as the properties of the materials. So here you can see we import the material name, density, Young's modulus, Poisson's ratio, maximum stress, and the price. So each of this material information will be used at different stages of this development process. And here we also import the loads from the specification sheet, and here you can see this is the different data that has been imported from the load sheet. So we have the multi-points information, which means the places where the rigid body elements have to be defined. So these rigid body elements will be used in the FEM analysis section, and followed by we have also the locations where this multi-points has to be defined. And we have the loading information here, the load vectors and their respective magnitudes, and we have the constraints, that means the degrees of freedom. What degrees of freedom has to be arrested at what locations. And here we also have the target stiffness and the stiffness type for the RBE definition. So this is all the input data, and this is the workflow with inputs and outputs. So here, as you observe, the inputs of this workflow are the containers which are colored in orange ones, and the outputs of this workflow are the containers in blue color like this. So what could be the use of this workflows with inputs and outputs? Well, if this workflow is used multiple times in different projects, one can simply make use of this workflow and include them in their respective projects or workflows. So let's move to our main workflow here and check out the next step. And here you can also see the outputs of this workflow. So here we have several outputs that are used for different stages. So let's go to the second stage here, where we have to create the design space based on the use case selected. So here we can go inside this workflow and check out how the design space is created. So this is the design space which has been created for our non-design spaces. So in this case we had like 8 suction cylinders, and hence the design space is adapted to it. If we had selected the non-design spaces with 6 suction cylinders, the design space should be created in a different way so that it adapts to the respective non-design spaces. And here you can also find a nice and useful feature to visualize the geometries. So one can also visualize the geometries inside the canvas and not just using the viewer here. So this is how we create the design spaces, and along with the design spaces we also create additional geometries in this step which will be used in the later stages. So let's go to our main workflow here. Once we create this design space, as you can see, it is nicely adapted also to the suction cylinders. We move to the next stage here, where we define the RBE connections. So here, as you can see, the inputs are the suction cylinders, vacuum plate, which are non-design spaces, the multi-points, which are the locations at which the RBE connections are defined between these geometries and the multi-points. And here we also have the stiffness type for this RBE connection, rigid or deformable. So for the supports, it has to be a rigid connection, and for the forces, it has to be a deformable connection. So you can also go inside this workflow and check out how these RBE connections are defined here, as you can see. So once we define the RBE definitions here, we have to go to the next stage to define the boundary conditions. So here, based on the load sheet that we have imported in the step 1, we will define the loads and the supports, and based on this we create a load case. So here you can see we have the loads and the constraints as input to this workflow along with the multi-points, and we have the output, which are the load steps. Along with it we have the evaluation nodes for the displacement that can be used in the later stages. So if you go inside this workflow, here you can observe that what are the different stages involved. So first we define the supports, which is at the center of the vacuum plate, and here we have the loads at the multi-points which are inside the suction cylinders. So if you visualize all together, this is how the load case looks like. So this is a linear static mechanical load case, and once we have the load case defined, we have to perform an FEM analysis. So if we go inside our main workflow here, we go to the next stage where we are performing FEM analysis. So what we have to do here is assemble all of this information, such as this load cases, RBE definitions, and along with it we have to also create the meshes for the part. So how can we do that? We can go inside this and see. So here we have the design and the non-design spaces, and we have to create the mesh which is required for the FEM analysis. So here you can see the mesh is using the hypermesh connector, which is from Altair. So in this case you can also use our internal mesher and create the mesh. So as you can see, this node is disabled now since we have the internalized data saved here. And once we create the mesh, we will define the solid part, as you have learnt, which means assigning material properties to this mesh, and then followed by assembling an FEM model here by defining these solid parts, RBE connections, and the load steps. And once we have an assembled model, we can solve using different solvers. So at this stage, this is an Altair Optistruct FEM solver, but one can also use different solvers such as ANSYS, Abacus, Nastran, or our own internal solver. And once we have run the FEM analysis, so in this case the models are internalized, but you can visualize the result here using this node model view, and here you can select between element stress, displacements or rotations. So once we have performed FEM analysis, the next stage is to carry out topology optimization. So now we go to the next stage. So here we have two different types of solvers that are used for topology optimization. As here you can see, we can select between HxGN Emendate or Altair Optistruct solver. So based on the type of optimization solver selected, the respective workflow will be used to perform the optimization. So if you go inside this workflow, as two solvers work slightly differently, the workflow is also a bit different. So at the top here you can see the workflow with HxGN Emendate, and at the bottom here you can see the workflow with Altair Optistruct. So based on our selection, the respective solver will be selected and the respective mesh is given as an output. So to understand how each optimization setup for Altair Optistruct and HxGN Emendate works, please check out this workflow in detail. So once we perform the optimization, we have the optimization mesh as you can see here. So this is based on the HxGN Emendate solver. So once we have the optimization result, we should be able to automatically reconstruct it such that it is nicely connected to this non-design cylinders and the vacuum plate. So how can we do that? Then we move to the next stage here to perform the topology reconstruction. So how does it work is we take the optimization outcome and then perform a boolean operations with the design and the non-design spaces. But how can this be so efficient is using our quadri meshing algorithm. So first we will convert the optimization mesh using the voxel operations using our own voxel engine, and then performing a quadri meshing of that, and followed by performing boolean operations with the design and the non-design spaces to achieve the final optimization result. So here you can see this is the reconstructed and the final optimized geometry. So far we have learned how to import the specification sheet which can contain the materials and the loading information, and we have learned how to create the design space which is automatically adapted to the different versions of the non-design space geometries, which are 6 and 8 suction cylinders, and then followed by assembling and performing FEM analysis to see how the part behaves. Later we have performed a topology optimization which is possible using two different kinds of solvers, and then automatically reconstructing the part such that it is ready for additive manufacturing. So at this stage we are basically done achieving the final part. But as you know, this part is a vacuum gripper. We also have another stage which is pathfinder. So at this stage what we have to do is create the pipes in this final optimized geometry that runs from the vacuum plate to the suction cylinders. So this has to be very short and also optimized. So how does it work? Let's go inside this workflow, and here you can observe that first we define the optimized geometry as an input to this workflow, and so this is input geometry, and then we have the start points which are these ones like you see, and we have the endpoint which is in the vacuum plate. So the start points start from the suction cylinders and the endpoint in the vacuum plate, and then here we use our algorithm pathfinder which gives out an optimal path between the start and the endpoints. So based on this we create the pipes in this optimized geometry. So please check out also the next stages. Once we extract the curves from the pathfinding, how do we post process so that the curve network is clean, and then how do we construct it to get the final pipes. So we can go to our main workflow here and visualize the gripper with the pipe channels. So here we can also make it look nice by applying colors. So here we can see that the optimized gripper is in green color, and here we have the pipes running from the vacuum plate to the suction cylinder. So this is our final optimized geometry. Now we have to perform some evaluations on this final part. So we will move to this stage and let's go inside this workflow now. So here you can see there are different stages of evaluation. First is to calculate the weight or mass of this part to see if it is within our acceptable limits. And then here we are calculating the production costs using LBM costing, and here we define the orientation of the part and the material price that we have imported from the specification sheet and also the density. So based on these values we get the cost of manufacturing of all of these parts in the given machine dimensions. And once we have the production costs, we can also create this simple line support structures that looks like this, and we can also include it in the cost calculation. And once we have the cost estimation of manufacturing of this part using laser beam melting process, we also have to perform another evaluation study, which is process simulation. So here we perform LBM process simulation using Amphion, which is the external add-in. And based on the simulation result, that is distortions and stresses, a predeformed part is also calculated to compensate the distortions. So here we can go into the main workflow. Since it takes some time to perform the simulation, the data is internalized and it is given as an output from this workflow. So here using this node Amphion result view, one can visualize the result here. So this is the displacement of the part. And once we are done performing all the evaluation studies, we can see the KPIs here and also export the final parts as an STL file or a step geometry for further studies or for PLM process. This is an end-to-end workflow for the development of an AM part, combining knowledge from different domains such as CAD, FAM, optimization and manufacturing. With Synera as your connected engineering platform, you have the ability to centralize all data, all knowledge, all information and valuable IP so that it is integrated across the systems. Now we invite you to dig deeper into the workflow or adapt it to one of your cases or one of your products. Thank you.